Okay, I'm going to start my today's session without further delaying. As you can see on your screen, that I'm going to present a new topic today, which is continuous probability distributions special case, and it is called a normal distribution. We have learned that probability distributions are of two types. One is discrete probability distribution and another is continuous probability distribution. We have also learned that discrete probability distributions can be categorized into different types. Two of that we have learned in our syllabus. One is the fundamental binomial distribution and another is the Poisson distribution, which is the special case of binomial distribution. Although I'm saying binomial distribution is fundamental, but it is not, because before binomial distribution, Bernoulli distribution was studied, and then the binomial distribution was developed, because a binomial distribution is a generalized version of the Bernoulli distribution. In the Bernoulli distribution, the part NCX is not there. That is the only difference. Anyways, apart from these two discrete probability distributions, there are other discrete probability distributions which haven't been studied in our class because those were not the part of the syllabus. So I have directly come to the continuous probability section. And the first special type of continuous probability function is called the normal distribution, where the associated random variable is called normal random variable. The normal random variable is the most fundamental, and it is the distribution which has beautiful characteristics, and also under certain circumstances almost every probability distribution tends to follow normal distribution. Normal distribution, the curve which the probability function has, you are not totally unfamiliar to the curve, because during the last year lockdown, that curve was in news. Many times news channels showed this curve. This year also you can see this curve in many parts with respect to the COVID-19 disease. So this particular probability distribution is very fundamental, and that will be studied, and this is the point which I'm going to discuss in my today's class. Now, first of all, as the note is showing you, let us read the definition of normal random variable as it is written in the note. Let capital X be a continuous random variable whose probability density function fx is defined as, okay, probability density function, if you can recall, that I told you that probability functions are named in two different ways, just to distinguish between the two types. When we talk about probability mass function, we understand by the name that we are actually in the domain of a discrete case. And when we call out the name probability density function, then we understand by the name that we are working in the domain of continuous distribution. So probability density function and probability mass function are not different from one another. They are only different by their names. Their characteristics are similar. One is associated with discrete random variable, another is associated with a continuous random variable. So let capital X be a continuous random variable whose probability density function fx is defined as, now you see a big expression has been shown over here. So let us read this expression first of all. Fx, the probability function, is given to be 1 by sigma root over twice pi. Now, this particular section is not properly printed, so I'm going to write it beside the formula so that you must note it down correctly. It would be 1 by sigma under the square root sign twice pi. This 2 and pi both are under the square root. Minus infinity to plus infinity is the range. The real number is taking variables, taking values from. Then we have e to the power exponent of minus half x minus mu by sigma whole square, okay, dx. And the variable x is taking continuous values within this range. So this is your fx. I have properly written it over here so that if I can see there are some misprints which can be avoided by that. When I talk about the mother variable, I'm using the sign capital X. It's the random variable. But whenever I'm writing the probability function, I'm using small x. So be careful about that. Okay. And just like the binomial probability function and a Poisson probability function, this probability function has also two parameters. Now, what are these parameters of this probability function? Let us try to identify one of the parameters. Okay, now you see 2 is constant, it's a number, it's an integer. Pi is irrational number, it's a constant. And under the square root sign, whenever I write twice pi, it is also constant. And e to the power something, if I put different values of x, you will get different exponents, okay, according to the expression given. This entire expression will be known and can be integrated only if we know the value of mu and sigma. If you do not know the value of mu and sigma, then you cannot integrate, you cannot know the function and you cannot integrate it. Also, sigma is appearing outside the integration sign as the reciprocal of it has been taken and being multiplied by the reciprocal of under square root twice pi. So it is pretty clear from this particular function that mu and the sigma, these are the parameters of the normal variable. Remember, this capital X, if it has such kind of probability function, such kind of expression, then such variable is called normal variable. Or sometimes people call it normal random variable. Or sometimes it is called normal variate. Variate is the synonym to the word variable. It is often used in statistics. The parameters of the variate, the normal variate, are mu, which we call basically the mean, and sigma is called the standard deviation. Just like in binomial distribution, we call NP to be the mean of the binomial variate and NPQ to be the variance of the binomial variate. Similar to that, in Poisson distribution, we call lambda to be the mean and variance of the Poisson variate. Here, we call mu to be the mean of the normal random variable capital X and sigma to be the standard deviation of the normal random variable capital X. And remember, if capital X has this kind of probability function, then sometimes we write X follows n mu sigma. We read it as X is a normal distribution with parameters mu and sigma, or sometimes we write X follows n mu sigma square. Why? Because sigma square is the variance and sigma is the positive square root of variance, which goes by the name standard deviation. So remember these things, okay? Let me scroll. Let me scroll down. Now you see, when we plot this probability function, we get this kind of shapes. Okay, these are the shapes that we got when we plot it. Now, all of these shapes, they look very similar, but only difference among these three shapes are, this is highly peaked, its peakness is very high, it is moderately peaked, and you can say that it is less peaked, or it is kind of flat curve. Okay, so let us write the characteristics just beside the curves. So this curve is highly peaked. This curve is moderately peaked. And this is a flat curve. These are the dissimilarities among these three curves. What are the similarities? If you look carefully, you will find that if you draw a vertical line, it will touch at the point 2. If you draw a vertical line, it will touch at the point 2. If you draw a vertical line, it will touch at the point 2. And you can say immediately that mean, that is mu, of these different functions, they are actually same. What is different is their standard deviation, the dispersion, the scatteredness of the point around the mean. That is different. Here the scatteredness is less, so you get less deviation on both the sides. Here scatteredness is kind of moderate, so you get some sort of deviation on both the sides. Here scatteredness is high, so you get same amount of deviation, but a large deviation on both the sides of this middle line. Okay, so from this particular example, we can immediately say that, we can immediately point that normal curves may be highly peaked, may be moderately peaked, may be flat curve, but they are symmetric about the ordinate. They are symmetric about the ordinate. What do we mean by that? We mean that number of points appearing on the left hand side of that is equal to the number of points appearing on the right hand side of that. Number of points appearing on the left hand side of this is equal to the number of points appearing on the right hand side of this. Number of points here will be equal to the number of points there, but this number of points are infinitely large. So actually we do not call them we do not call it number of points. We say that left hand side of the curve contains 50% of the total area in all these three cases. Right hand side of the curve contains 50% of the total area, and it is true for all these three curves, so that the total area, if we integrate it from minus infinity to plus infinity, this should be equal to 100%, that is 1. So in terms of percentage, the total area is 100%, left will contain 50% and right will contain 50%. And in terms of probability, the total area will be unity. Left will contain 0.5, right will contain 0.5. In many ways, we can define this particular curve. Okay, and also remember that the highly peaked curves, highly peaked normal curves, are sometimes called leptokartic curves, Moderately peaked normal curves are called mesocartic curve, and flat curves are called platycartic curves. These are the different names. These are the different names which are actually given to different types of normal curves with respect to different deviations. Now you can see that what are the relevance of these curves. As you can see, this is the peak point. Now suppose if you want me to analyze the situation, that what does this actually mean, and probably you have seen in television that suppose I can set a date over here, a date over there. Let us call this date from, say for example, let us consider today is 5th May. So I'm considering, say for example, 26th April. Okay, so I'm putting here 26th April. And suppose here I'm writing 26th July. Somewhere in between this range, this COVID-19, the number of people affected by COVID-19 or COVID-19 virus will be highly peaked. That is the peak point. And definitely after that time, we can expect that it will, that particular number of infectious people will go down. And it always happens. Virus takes the number of virus, whenever a new virus comes, it actually increases, it reaches to its peak point at certain point of time, and then it actually goes down. So this is the peakness of the current situation of COVID-19 in India. Whatever maybe the reason is, that is the thing. You can say, now these things, these different curves can also be studied in the same, with respect to, say for example, same COVID-19 disease. You can say that probably this is the situation of India, this is the situation of England, and suppose at present, this is the situation of Vietnam. Okay. Now, this, and also I must mention that the word Kartik, which is present over here in every name, like leptokartic, mesokartic, platykartic, this word Kartik comes from the term kurtosis. And we shall study kurtosis in due time. We have the study of kurtosis in our syllabus. Okay. So let us now scroll down further and let's see what else is there. Okay, now I think I have to remove these writings, otherwise you'll not be able to see it properly. I hope that you have copied the relevant portions. Since I have prepared the note, and if I frequently change the sharing screen from PDF file to whiteboard, then it will just kill the time. So I have to write something on the page itself. Okay. Now, let us do a little bit of numerical analysis. What is that numerical analysis? First of all, you have numeric. I don't know whether you have numerical analysis in your syllabus. If it is not there in your syllabus, no, probably in the second semester numerical analysis is not there, but in the coming semesters you may study numerical analysis somewhere in some semester. So this, look at this probability function. What this probability function is doing, this probability function is actually integrating, this probability function is actually integrating from minus infinity to plus infinity, and it is integrating this particular function, exponent of minus half x minus mu by sigma whole square. Now, for the sake of our studying the probability function, we can do one thing over here. We can introduce one another variable into the picture. And remember that in normal distribution problems, we do not often work with normal random variable capital X. We, rather than that, we work with standard normal variable. Standard normal variables are actually denoted by capital Z, and it is defined from the normal random variable by the definition as has been highlighted over here. Standard normal variables are defined as capital X minus mu by sigma. What does that mean? Nothing. We are just actually changing the scale from 0 to mu, and we are not changing the scale, we are changing the origin from 0 to mu, and we are changing the scale to sigma. So that is this change of origin and scale. When we apply this to the normal random variable, we get a new variable which is called standard normal random variate. Okay, and then with respect to this, the shape of the curve actually doesn't change, but what changes is the following. So if I do so, we get a normal curve like this. My drawing is bad. Okay, we have to draw it in a way so that this must be equal to the right hand side. And in the previous case, which I drew earlier, which I showed earlier, origin were somewhere on the left hand side. Now, since you have shifted your origin to mu, now that has now become your origin. Originally, when we talked about capital X, this was the point which we termed as the mean. Now we have shifted the origin from left hand side to the point as the new, in terms of new variable, that mu has now become your origin. So if you get the origin in the middle, then it is often becomes easy for us to study the system properly. Okay, we can calculate the things very properly. We will be able to draw diagram, we'll be able to study the coordinate distances only when we know the origin. So we have to draw the origin first of all. Now, with respect to this curve, we didn't know where the origin were lying. So probably at the time of calculating the things, we will not be able to find out the actual value. But if I shift the thing to the middle, then my origin, the origin of the function is in front of my eyes, then we can at least say that left hand side contains the negative points of Z and right hand side contains the positive points of Z. And this range is also from minus infinity to plus infinity. Here also in terms of X, it was minus infinity and plus infinity. And remember, this curve, both the tails of the curve will not ever touch the x-axis or here the z-axis in reality. It will touch the curves, the curve will touch the horizontal axis on both sides at infinities. And if you can recall, such type of axis which touches the curve at infinity, either plus infinity or minus infinity, such curves, such lines are actually called asymptotes. So here you can say both the horizontal axis are asymptote to the normal curve. So it is a very important point. Horizontal axis in both cases are asymptotes of the normal curve, normal or standard normal curve. Note it down. Very important point. Now, you can see that this probability in the probability function fz, this sigma isn't present over here. So is it a mistake? No, it is not a mistake. So I'm going to show you why this sigma is not present here. And I'm going to do the calculation on the left hand side. Since we have defined the standard normal variable by this, and we know that when we have the normal variable capital X, the mean of the normal variable is mu and variance of the normal variable is sigma square. We know it. Now, when we change the normal variable from X to Z, the question is, what will be the value of Ez and what will be the value of Vz? So we are going to calculate this Ez and Vz from the given expression. Now, your Ez is actually expectation of X minus mu by sigma. Now you know very well that we can take 1 by sigma outside the summation sign, and we can write it as this, E of X minus mu. What is the meaning of this, E of X minus mu? We can do it in two different ways. We can say that this is the average of deviations of the values taken from mean. And we know the average of deviations of the values taken from mean is always 0, because sum of the deviations of the values taken from mean is always 0. Okay? Or you can do it mathematically by applying the expectation rule. You can apply expectation on both the terms, and you know that already by definition Ex is mu and expectation of constant is constant, so this is mu, and therefore the result is 0, and therefore the origin has shifted to 0. Therefore the mean of the standard normal variable is 0. Remember, if standard normal variable has mean mu, the standard normal variable has mean 0. Okay, this is one part. Let us try to find out the part which will give us the value for Vz. I'm going to erase the right hand side. I hope that you have already copied it. Okay, now Vz can be written as E of Z square minus Ez whole square, but you already know that Ez is 0. So here in this case, Vz will be simply be equal to Ez square. Now Ez square, we can calculate this as follows. It would be equal to E of X minus mu by sigma whole square. Now this is equal to E of X minus mu by X minus mu whole square, and 1 by sigma squared will be, this is 1 by sigma square is the constant, it will come outside the expectation sign. Now carefully observe that we can write it as E of X minus, just a minute. I have to remove this. Oh, okay. We already know that we can write it as E of X minus, mu can be written as Ex whole square. And if you can recall this expression, this expression is nothing but v of x. And we know that v of x is sigma square itself. So E of z square is actually coming out to be 1. And since E of z square is coming out to be 1 and it is equal to Vz, so this will be equal to 1. So we have got that Vz variance of z equal to 1 over here. And therefore, in the probability function, what was the probability function? The probability function was f of x 1 by sigma root 2 pi e to the power minus half x minus mu by sigma whole square. Now, since we have considered z equal to x minus mu by sigma, so small z will be equal to small x minus mu by sigma. And consequently, this will imply that f of small z will be equal to 1 by 2 root over 2 pi, because sigma will not be there, because in terms of z, sigma equal to 1, because Vz is equal to 1 e to the power minus z square by 2. And that has been written over here. Therefore, the expression looks like this. Okay. Now, quickly copy the right hand side because I'm going to erase it. I'm erasing the left hand portion. So I have shown you that when I change the normal variable to standard normal variable, the expectation of the standard normal variable becomes 0, and the variance of the standard normal variable becomes 1. Okay. Now, what can we say about the normal variable? We can say about this probably normal variable or standard normal variable is that we have got many characteristics of this curve. This curve is a symmetric curve, as you can see. Horizontal axis is the asymptote to the curve. The curve is a bell-shaped curve. The curve is a bell-shaped curve. And another interesting point is that x equal to mu or z equal to 0, these points are known as mean, median, or mode of the normal curve. Why? It is mean because by definition it is mean. It's median because median actually divides the entire region into two equal halves. And since the left hand side of that contains 50% of the total area, right hand side contains 50% of the total area. So therefore, this point x equal to mu, here I have written in terms of normal variate, is actually the median. If you write z equal to 0, then also it is the same thing happens over there. And why it is mode? Mode is the point which is associated to the highest frequency. Mode is the point which is associated to the highest frequency, and therefore the peak point it is appearing over here. The peak point is appearing over here, and therefore this point, the point at which the frequency or the probability is maximum, is called the mode of the distribution. So remember this point. So we can call it as we can call mu to be mean of x, or median of x, or mode of x. Mean, median, mode of the normal distribution coincide at a single point. This particular point is very important. You just note it down in your copy. So I'm going to erase the right hand side. Okay. Now let us scroll down a bit. As you can see that I have drawn a figure over here, a figure of normal variable. And in this figure, you can see that I have written x equal to mu, and some other points have been described, have been shown in the figure. That is mu minus sigma, and at an equal distance, we have written mu plus sigma. Here I have written mu minus 2 sigma, and here I have written mu plus 2 sigma. Here I have written mu minus 3 sigma, and here I have written mu plus 3 sigma. And some values have been shown over here. What are these values? This value says that, look at the value carefully, and that thing has been explained on the next page. Okay, this is the thing which I have shown in the figure. Just carefully observe. I am actually calculating the probability that x is lying between 2 points, mu minus sigma and mu plus sigma. Now what you can do, as I told you, to calculate the probability, to calculate this kind of probability, what we actually do is that we can transform the variable x to the standard normal variable z. And to do it, you have to subtract mu from x, and you have to divide by sigma. You can divide by the sigma, but the inequality will not change because sigma is a positive quantity. Okay. And since it is an inequality and you are going to change this variable x to z, so you have to subtract mu not only from the middle, but from all the sides of the inequalities. This is a school mathematics, which I'm not going to explain. And after this transformation, we get z in between 2 points. One is -1, another is +1. What do we mean by that? This means actually we are going to integrate this function 1 by root over 2 pi e to the power minus half z square dz from -1 to +1. Do you have to integrate here in the course of probability? The answer is no. So what you can do, how can we know these values? Actually, these values are known. Actually, these values are known by integrating these functions, but the integration may become a little bit complicated. So we actually go for numerical integration. There are various methods, and we actually help students to solve them in the practical class. Some of the methods are such known as a trapezoidal rule, then Simpson's 1/3 rule. By this numerical integration method, we can actually calculate this type of complicated function. We can integrate this type of complicated functions. And if you integrate this, you will get the probability to be 0.68. Similarly, if you consider mu minus 2 sigma and mu plus 2 sigma, you will get 0.95. And for the last one, you will get, for the last one, you will get 0.997. So these are the values which you have to memorize, to calculate further probabilities, because these are the very fundamental probabilities in case of normal curve, and they are called area properties. So I'm going to stop over here. We shall again meet in the next session.